Hey there, we're discussing section 5.4. The second half of these notes start in the middle of page 4. So here are optimization problems in which the extreme value theorem would not apply. So we're going to talk about how to approach those kind of problems. So here's example 6. You're asked to find the smallest perimeter rectangle with the following area of 20 square meters and to give us dimensions. So remember, whenever we're dealing with optimization problems, you want to assign your variables as probably a first step. So we could probably call one dimension x and this one y. And we have our conditions. So our conditions will be that the area must be 20. Remember, area is length times width, or 20 equals x times y. So that's a condition that we must have. Now here's the problem though. The domain is going to be tricky for x. X, for example, won't be negative because we don't have a negative dimension, but it's not going to be 0 because 0 would then lead to a 0 area, and obviously the area is 20. It could be really close to 0, like x could be like 0.001, and y could be really big. That is possible, but it's not going to be a closed interval. And x, in fact, could be infinity. So in this case, this is not closed. And because it's not closed, EVT won't apply. Now, what we're trying to optimize here? We're trying to optimize the perimeter, right? And perimeter can be defined as 2x plus 2y. And of course, we're going to want to substitute, so let's get y by itself here. Y equals 20 over x. And we substitute, p equals 2x plus 2 times 20 over x. So perimeter is 2x plus 40 times x in negative 1 power. Take the derivative of both sides with respect to x, so dp over dx equals 2 minus 40 times x in negative 2. And of course, we set our derivative equal to 0 because that's where we have critical points. Solve for x, algebraically, which you guys should be pretty comfortable doing. And if you move things around and do everything correctly, you should get plus or minus root 20. Now, of course, x is not going to be negative, so we'll just go 2 root 5, actually simplifying that radical as well. Now, because extreme value theorem does not apply, we can't really do that test of endpoints or critical points like we used to for the previous examples in these notes. So what we'll do instead is we'll do a first and we'll do a first derivative test, and we'll also evaluate its concavity. And you'll see why we're going to do that in just a little bit. Okay. So if we take our first derivative function, which is this right here, and also 0 is a critical point too, so we'll just look at 0 and 2 root 5. If I play anything bigger than 2 root 5, say like 5 or 6 or anything like that for my derivative, I know it's going to be positive here. And then if I play like 1, for example, my derivative will be, sorry, I take it back. No, I was right, it was positive. If I plug in something between 0 and 2 root 5, say like 1 or 2, it's negative here. And it'll still be negative if I were to plug anything over here. But we're not looking at negative dimensions, so it's not even worry about that. So what happens is that this becomes a relative min because it changes from negative to positive at 2 root 5. Still, that's not enough for us to say it's an absolute min. So how do I know it's an absolute min? What you do is you do a second derivative. So if you do the second derivative for perimeter, that will be, remember, perimeter was 2 minus 40 times x in -2 power. So second derivative will be 80 times x in -3 power, or 80 over x cubed. Now, in the interval, or whenever x is bigger than 0, because 0 will be definitely a critical value for the second derivative, negative and positive. But we're always concave up in that interval here. So if you're always concave up and you have a relative min, then relative min then becomes an absolute min. And that's how you can prove that we have the smallest possible perimeter when x is 2 root 5. And then to get all the dimensions, 2 root 5 by, I believe, 2 root 5 as well, because that does multiply out to 20. And so that would be my dimension. And my smallest perimeter, of course, would be 8 root 5. And it so happens that the square actually achieves that for us, in case you're curious. So, okay, so that's that one. And so just to summarize, if you do not solve using EBT, do not just assume that a critical point will automatically give absolute minimum or maximum for your function, even though most likely it will. In order to prove it, you're going to want to show that's a local minimum max using a first or second derivative test up to. I did a first derivative test. Second derivative test, what you do is you'd find the critical point and then do the second derivative and see that, okay, you know, it's concave up or down there. But really what we want to do, and then of course, establish whether it's concave or concave down everywhere in its domain. So personally, what I would do is just I would, you know, find the local min, find its local min or max using the first derivative test, and then establish its concavity. And that's going to be the safe thing to do. And if there's just one critical point of the domain, and you've established the local max or min, you could probably assume that's absolute max or min. If there are two, and one's max or min, then local max would be absolute max, local min would be absolute min. We could assume that also. But just to be sure that you work these parts out as well. So here we're just going to set up example 7, 8, and 9. And then we'll end the lesson here. So in this case, you have a rectangular pea patch, so you're growing peas, 216 square meters, divided into 2 equal parts by another fence parallel. So another fence. Okay, let's make it more equal. Well, what dimension for the outer rectangle will require the smallest total length fence? So that's x. Actually, I'll call this y, y, y. I'll call this x. I'll call this x, right? So our perimeter actually is going to be 2x plus 3y. Now our area, of course, is x times y, or 216 equals x times y. And we could probably do a substitution, y equals 216 over x. And again, our domain for x is still from 0 to infinity. And then, you know, the perimeter in terms of x would be this, 2x plus 3 times 216 over x. And then, you know, just go through the same motions like we did for example 6. So that's how I'd set it up. For example 8, you have an open top cylindrical can that hold 1,000 cubic centimeters of liquid. Will be the dimensions that use the least amount of material. So we want to minimize our surface area, actually. That's what we want to do. So our condition, 1,000 equals pi r squared h. Probably easier if I isolate h. And remember, it's an open top, so we'll get the surface area in terms of r. So we pi r squared plus 2 pi r times 1,000 over pi r squared. Fortunately, lots of things cancel, and we could simplify further. S of r is going to be pi r squared plus 2,000 times r to the negative 1 power. And then again, you take your derivative, set equals 0, do the first derivative test, and then check the concavity, and you'll be able to verify that your critical point for r when the derivative equals 0 for the surface area will be the dimensions you want for the least amount of metal. And the unit selecting will be centimeters for that. Finally, example 9. Again, we have volume, and it's a square base of x and x, height's y. Volume will be x times y, or 20,000 equals x squared y. So y is 20,000 over x squared. Now, you want to reduce the cost, right? Your cost function in terms of x and y, apparently you're charging $1,000 per square meter for the sides. The sides are x times y, and you got 4 of those sides. And then for the base, it's $800, and the base is just x times x. So if you replace y with 20,000 over x squared, you get 4,000 x times 20,000 over x squared plus 800 x squared. That'll give me the cost in terms of x. If you reduce it a bit more, you get 800 million. No, I lied, 80 million, which is a really big number, of course, times x to the negative 1 power plus 800 x squared. And of course, take the derivative of both sides with respect to x, so set equal to 0, get your critical values, do the first derivative test, check the concavity, and you'll be A-okay. Okay, so that concludes the lesson on section 5.4 for the second half of these notes.